Welcome back to the Deep Dive. We've got a fresh stack of sources today, and we're taking you right to the cutting edge of post-production and digital content creation.
We are.
We're diving deep into something that has felt tantalizingly close for a while now, but just out of reach for, real commercial applications, perfect production-grade video object insertion, or VOI.
Yeah, this is really the holy grail for generative AI, especially in fields like film, television, and particularly high-end product advertising.
Mm-hmm.
I mean, just imagine shooting a scene quickly and then in post being able to drop in a perfectly scaled, flawlessly lit object. It could be a specific brand of espresso machine, a new shoe design, an art piece.
And have it just work.
And have it interact realistically with the entire 4D environment of that scene.
The operative word there is definitely realistically.
Yeah.
Because diffusion models, they've given us this incredible raw ability to generate video, but achieving that level of, let's call it seamless integration, making the object look like it was actually there when the scene was shot, that has proven to be incredibly challenging for all the mainstream tools we see hitting the market.
It really has. When we look at the advanced commercial tools, things like Pica Pro or Kling, they are fantastic for, creative prompting and general video generation.
Oh, sure.
But reliable VOI, where the object maintains a precise scale, a consistent pose, and critically handles complex movement and occlusions.
Like someone walking in front of it.
Exactly. That still feels less like engineering and more like high-risk magic that frankly often breaks mid-clip.
And that failure point, it almost always boils down to geometry, right? The models are just brilliant at visual aesthetics, but they don't seem to fundamentally understand the spatial or temporal physics of the scene they're working with.
That's it in a nutshell. They might know what a coffee cup looks like in 1,000 different styles, but they don't know where that cup actually sits in the three-dimensional space of the video.
Or how that space changes over time.
Right, which is the crucial fourth dimension, time. If you move the camera, the object needs to adhere to all the laws of perspective and movement, and that's where these purely generative models so often just fall down.
So our deep dive mission today is centered on a framework that was designed specifically to conquer this production quality challenge. It's called InsertAnywhere. And this is a system that, from what I can tell, decides to stop guessing about object placement and actually start calculating it. It blends a deep 4D scene geometry understanding with diffusion-based synthesis to produce results that are, finally suitable for high-end commercial use.
It's a really pragmatic and, I think, beautifully layered approach. Their core thesis is that commercial quality demands you solve the geometry problem first.
Get the physics right before you paint the picture.
Exactly. Create a perfect, physically accurate blueprint. And only then do you move on to solving the appearance problem, synthesizing the photorealistic result. They explicitly decouple those two major challenges, and I think that's what gives them their robustness.
Okay, so let's unpack this. Before we get into the step-by-step process, what are the two core innovations that let InsertAnywhere get past these hurdles that, seem to stop the big commercial baselines?
Okay, so there are two major technical leaps that really define their advantage. First, it's the 4D-aware mask generator.
The mask generator.
Yes. This thing is responsible for basically decoding the scene's geometry, handling complex camera motion, and resolving occlusions not just creatively, but robustly and precisely. It creates a guaranteed coherent spatial map for the object to live in.
And the second innovation, I'm guessing that addresses the lighting and texture problem.
That's right. The second is the Illumination-aware dataset they built called ROSE++I. This dataset actually lets their fine-tuned diffusion model learn the physics of light and shadows.
So it's not just guessing.
It's not just painting generic textures inside the mask. It's learning how light interacts with surfaces and materials. And those two innovations together, the geometric precision on one hand and the learned photophysics on the other, that's what defines their pathway to commercial-grade VOI.
Let's start by really framing the difficulty for everyone listening. Why does achieving commercial quality VOI, and we mean, zero artifacts, integration so seamless you genuinely can't tell it's inserted, why does that present this complex dual challenge?
Well, commercial quality isn't just about having high-resolution pixels. It's about reliability, controllability, and most of all, physical accuracy.
Right.
If you're inserting a high-value product for a global ad campaign, you need absolute certainty about its position, its scale, how it's catching the light. So the dual challenge is that you have to solve accurate 4D placement, which is the geometry and high-fidelity video generation, the appearance and lighting, and you have to solve them simultaneously.
And historically, models are usually good at one or the other.
Or they try to merge them into some big end-to-end system that just fails when you push it.
Okay, so let's focus on that first problem. Geometric consistency in 4D placement. If I give an AI a beautiful high-res picture of a glass sculpture, how does it know how big it should be in the scene? Or exactly where to put it relative to a moving camera?
And that is the initial user control headache. That single 2D image, it has no inherent scale, no pose, no depth information needed for a 3D environment. So the first requirement has to be explicit user control.
So the artist has to step in.
The user has to specify the object's position, its size, its rotation, but only in the first frame. But honestly, that's trivial compared to the next challenge, which is propagation.
Propagating that placement across the entire video clip while the camera is potentially, zooming, panning, or tracking a subject.
Exactly. The object has to move consistently with that camera trajectory. It has to maintain correct perspective shifts and parallax throughout the whole video. We call that temporal coherence. But the truly difficult geometric challenge, the one that sinks most simple approaches, is occlusion.
Occlusion. Hiding and reappearing. This is where AI often just breaks down and you get those jarring, floating artifacts.
Precisely. The source material really emphasizes that existing methods struggle immensely when the inserted object is partially covered by, or then reappears from behind, other dynamic elements in the scene.
So let's use an example. Say you insert a piece of luggage onto an airport trolley in a video,
Okay.
and then a busy traveler walks quickly past that trolley. The AI has to recognize that the traveler is closer to the camera, and then accurately, frame by frame, block out the part of the suitcase they're covering, and then make the suitcase reappear perfectly as they pass.
And if a system fails to account for that depth and visibility, the suitcase just looks like a flat cutout that's floating in front of the moving person.
And the whole illusion is just shattered.
It creates what looks like a terrible amateur editing error. And the challenge is that your mask generation has to explicitly account for those visibility changes over time, and it can only do that if it has a reconstructed model of the scene's depth. Simple 2D tracking or mask propagation just can't handle those complex depth interactions.
Which is why the InsertAnywhere approach has to solve the 4D geometry first. It builds the map before it places the treasure.
That's a perfect way to put it.
So, okay, let's transition to problem 2. Appearance and local variation. We've established geometry is crucial. Let's assume InsertAnywhere generates a perfect, time-consistent mask sequence, a perfect hole for the object to go into. Why can't a standard video diffusion model just, color in the lines and get photorealism?
Because treating the task as simple video in-painting, just filling that defined mask area, it completely ignores the physics of light. When you insert a physical object, it's not just the object itself that changes the scene. It's the object's interaction with the entire environment's light field.
We're talking about those really subtle local variations, the things that sell the physical presence of an object.
Absolutely. Think about all the local effects. The soft shadow extending from the object onto the floor or the wall, the little specular highlight on a glossy surface that's catching the room light.
Or even the color temperature of the room affecting the object.
Exactly. If you insert a bright red handbag into a dimly lit, warm-toned corner, and the model just paints a generic, neutrally lit red handbag, it looks photometrically pasted in. It doesn't belong, even if it's sitting in the perfect 3D spot.
So the diffusion model needs to be an illumination simulator as much as it is a texture generator.
It has to be. And standard training methods for video generation or simple in-painting, they don't explicitly supervise the generation of these photometric effects. They learn to fill holes with plausible textures, not to model physical light interaction. That inability to generate realistic shadows and reflections is exactly why the baselines fall short.
And this brings us right back to the commercial tools like Pika Pro and Kling. The assessment from these researchers suggests their fundamental failure isn't one of generation quality, but of spatial and photometric reasoning.
That's the key takeaway. Those commercial models are primarily text-driven. So you might type a prompt like, insert a small pepper shaker next to the coffee cup. But the model lacks the explicit spatial reasoning to correctly infer the pepper shaker's true scale relative to the cup, or its exact pose, or the scene's depth map.
So it's just guessing based on its training data.
It's guessing, and that prevents them from achieving the robust, reliable, and physically consistent placement you need for a production pipeline. The qualitative evidence they compiled shows these tools repeatedly introducing geometric artifacts, incorrect scale, and often generating objects with colors that don't match the reference image or the ambient light.
Okay, so let's turn to the solution. InsertAnywhere solves that geometric challenge first. It creates the perfect mask sequence before any diffusion synthesis happens. This two-stage approach seems absolutely fundamental to their success.
It is fundamental. The first stage is entirely dedicated to creating a geometry-aware blueprint that guarantees user controllability and scene coherence. You're adjusting physical parameters, not just, painting a mask with your mouse.
So, step 1, 4D scene reconstruction. How do they take a standard video clip and turn it into this rough but temporally consistent interactive 3D environment?
Well, they rely on an orchestration framework, which is often referred to as the Uni-4D paradigm. It's basically a finely tuned orchestra of specialized, pre-trained computer vision models.
So it's not one giant network.
No, it's not about training a single giant network to do everything. It's about making multiple experts work together in harmony.
Okay, so what are the primary instruments in this orchestra? What does it need to know?
You need 3 things working in perfect sync. First is depth estimation. That gives you the geometry of the scene, which surfaces are near and which are far. Second, you need camera pose recovery. This tracks the camera's precise movement, the path it takes, its orientation, frame by frame.
And the third?
The third is optical flow. This captures the 2D pixel movement of any dynamic elements in the scene, like a person walking or an object moving.
So by combining all those outputs, the depth, the camera path, and the local movement, they can recover a single, cohesive 4D representation that tracks everything jointly.
Precisely. And this foundational reconstruction is what allows them to move beyond simple 2D masking or just global camera tracking. It gives them the spatial map they need to correctly handle parallax and occlusion for every single frame of the video.
So once that 4D space is mapped out, the user takes over for step 2, user-controlled object placement. This is where the geometric constraints get applied.
Correct. The user starts with their input object image, the eye of JDOL. Since the system needs a 3D object to place into its 3D map, they first convert that 2D image into a 3D point cloud, which they call nullers, using a specialized single-view reconstruction network.
So you can think of that as just creating a basic digital model of the object.
A very basic one, yes. And now for the interactive part, instead of just dragging a flat image around, the user is actually aligning this 3D model inside the scene's reconstructed 4D space.
Okay.
Yes. Through an interactive UI, the user applies a rigid transformation to that object point cloud. They get to control the scale, the rotation, that's yaw, pitch, roll, and the translation, offset, XYZ.
And this explicit 3D positioning is what solves that fundamental scale and pose ambiguity that just ruins the text-only insertion models.
It completely solves it. The user is telling the system, with precision, the object must be exactly this tall, facing this direction, and sitting right here in the world coordinates.
That seems absolutely critical. I mean, text prompts can only go so far. A user needs that absolute visual feedback and fine-grained control, just like they'd have in professional VFX software.
It's completely non-negotiable for commercial quality. If you're inserting say, a $10,000 watch into an ad, you need to make sure the face is angled perfectly to catch the light. And that's a rotation problem that only explicit spatial control can solve.
Now, for what I think is the most fascinating part, Step 3. Scene flow-based object propagation. So if the camera is static and the scene is static, the object stays put in its 3D coordinates. Simple enough.
Yeah.
But what if the table the object is sitting on is actually being moved by a person in the shot?
This is the aha moment. This is the truly dynamic challenge. If you simply fix the object to its initial world coordinates, it's going to look like it's sliding off any moving surface.
Right.
Imagine inserting an elegant pen into a small notebook that a person is actively flipping through and moving around. The pen has to stay perfectly synchronized with the notebook's local movement. The system has to obey local scene dynamics, not just the global camera movement.
Wait, so if we already mapped the whole 4D scene back in step 1, why is this extra step of tracking based on local flow vectors necessary? Couldn't we just fix it to the nearest static 3D point on the table?
That's a great question. The global 4D reconstruction is a foundation, but it can often be noisy, especially for small, fast, highly dynamic local movements. If you were to rely purely on that noisy global map, the inserted object might slightly lag or jitter relative to the moving surface right beneath it.
So you need high-frequency, super reliable tracking of that local movement.
Exactly. So what they do is employ a state-of-the-art optical flow technique, specifically a module called SERFT, to compute dense 2D flow across the scene, mapping how every single pixel moves from one frame to the next. But here's the trick.
Okay.
They don't look at the whole scene. They identify the nearest 3D points around the inserted object's center point in that first frame.
So it's looking specifically at the floor or the table or the person's hand surface right next to where the object is placed.
Exactly. It uses those nearest 3D points, the surrounding surface, and it projects them onto the 2D image plane to find their corresponding 2D flow vectors. Now, those 2D motion vectors, which indicate exactly how that surface is moving, are mathematically lifted back into 3D space.
That's brilliant.
This gives them a set of high-fidelity, local 3D motion vectors that approximate the scene flow only in that immediate vicinity.
So it's like checking the motion of the blades of grass right beneath a soccer ball to see if the ball should be rolling. It's using the immediate visual evidence.
Precisely. The object's center point is then updated based on the average of all these aggregated 3D motion vectors. This aggregation strategy ensures the object's motion is stable, physically meaningful, and critically driven by those local scene dynamics. That's how they handle complex scenarios, like an object on a moving serving cart or a jacket placed on a person who is walking.
Okay, and that brings us to the final step in the geometry stage, step 4. Camera-aligned reprojection. We have the object correctly positioned in the 4D world across time, it's moving accurately. Now we need the geometrically perfect 2D mask for every single frame.
Right, the final step is projection and rasterization. The continuously updated 3D points of the object are projected onto the 2D image plane of each frame. And to do this accurately, they use the recovered camera parameters.
Could you just quickly clarify for listeners what the system needs from the camera parameters to make that work?
Certainly. It needs the camera's intrinsics, which they call dollars, and its extrinsics, which is penidols. So the intrinsics are things like focal length, sensor size, lens distortion. They tell the system how the camera sees the world, its fixed property.
And the extrinsics?
The extrinsics tell the system where the camera is sitting in 3D space, its position and its orientation in world coordinates, and how that changes over time.
So using both sets of parameters ensures that the 3D object is projected onto the 2D plane with the exact correct perspective and parallax shifts for that specific moment in time.
Exactly. In this projection, it accounts for camera movement, parallax, and the crucial step of occlusion. Since the object is defined in 3D relative to the scene's 3D map, when the system renders the 2D mask, any existing scene element that is closer to the camera will automatically block the object's rendered silhouette.
And that's the output.
That's the output. A geometry-aware, temporally consistent binary mask sequence that is ready to condition the diffusion model. This is the solid spatial foundation upon which photorealism has to be built.
Okay, so we've built the perfect geometric placeholder, the precise mask sequence. Now we pivot to the appearance stage, filling that mask with an object that looks photorealistic and, crucially, interacts correctly with the scene's lighting.
Right.
This is where the diffusion model, specifically the fine-tuned 12.1 VCE 14B model, takes over.
And that fine-tuning is absolutely key. They use LoRa, which is a technique that lets them efficiently adapt a large, pre-trained video model to the specific domain of object insertion, and they can do it without having to retrain the entire foundational network from scratch.
Which saves a huge amount of computational cost.
Immense. And they also employ a first-frame anchor strategy to ensure high fidelity right from the start.
Explain that a bit more. What's the thinking there?
It's a really crucial design choice. The researchers acknowledge a simple truth in generative AI right now. Image and painting models generally have higher visual reconstruction fidelity and higher resolution than video models do.
Okay.
So they dedicate resources to generating that initial frame one result with extremely high fidelity using established image object insertion priors.
So frame one is the high-quality gold standard for the rest of the clip.
Right. That initial frame then serves as a reliable visual anchor. It maintains the consistent appearance, the color, the texture, the initial lighting, which is then propagated and maintained throughout the rest of the video sequence. It stabilizes the identity of the inserted object.
But the real innovation here isn't the model architecture itself, it's the data that the model is trained on. We talked about that photometric problem earlier, the shadows, the reflections, and how standard data sets don't supervise those effects very well.
And that's the core obstacle for the diffusion model. Training video object insertion is notoriously difficult because ideally you need 4 highly consistent components for every single training instance.
What are the 4?
You need the video without the object, the video with the object, the precise mask sequence, and the clean, high-fidelity reference object image. Acquiring all 4 of those in the real world with perfect consistency is, well, it's virtually impossible.
Because even if you film a scene, move the object out, and film it again, the ambient light will have shifted slightly. The camera might be off by a millimeter.
A shadow might move, anything. And prior self-supervised in-painting approaches, they just lacked the explicit supervision for lighting and shadow consistency. They learned to fill a hole, not to model physics.
Which leads us to the critical dataset innovation.
Yeah.
Rose plus whale. Now, they didn't go out and film thousands of new scenes. They did something clever. They inverted an existing dataset called Rose, which was originally made for object removal.
It's a very clever inversion strategy. They took the object removed video and they called that the source video. And they took the object present video and called that the target video.
Yeah.
By training the diffusion model to map the source, which has a hole, to the target, which is filled, they turn an object removal task into a supervised object insertion task. And that provides the spatial and temporal ground truth they need.
But they still needed that final component, right? The reference object image to augment the pair into a triplet, which gives us the plus in Rose plus. This is where the VLM comes in.
Right.
So why use a vision language model to generate the reference image? Why not just crop the object from the existing video frames?
This is a really crucial detail that addresses a known failure mode of previous research. Methods that just cropped objects from random video frames led to 2 huge training issues.
Okay.
First, you get overfitting to the video's specific lighting, its noise, its context. And second, you get the generation of really obvious copy and paste artifacts because the model hasn't learned how to generalize the object's appearance under new, unseen lighting conditions or from slightly different viewpoints.
So the VLM-based object retrieval process ensures the model learns from a consistent, high-quality, almost canonical representation of the object, completely decoupled from the video noise.
Precisely. It's about creating the ideal product shot every time. The process itself is surprisingly rigorous.
So for a specific training clip, they'll sample multiple frames, say no frames, and extract the object crops. Then they feed these multi-view crops to a powerful vision language model like GPT-4, along with a really strict detailed prompt that basically acts as an art director for a product photographer.
And the key instructions in that prompt are what define the quality of the output. The VLM is instructed to generate null candidate images on a pure white background. It has to preserve the object's exact proportions and fine visual details. But here's the clever part.
Okay.
It has to use multi-view reasoning to reconstruct any missing or obscured parts of the object realistically and maintain consistency in geometry, color, and texture across all the multiple views provided.
So it's synthesizing the object's ideal full 3D form from just a few limited 2D views.
Yes. It creates a robust canonical reference image. Then they use Dino-based similarity metrics. Dino is a type of self-supervised vision transformer to rank these candidate images against the original object in the source video.
And why Dino? Why not just a standard pixel comparison?
Because Dino measures perceptual similarity. It looks at high-level features and identity, not just pixel-by-pixel color matching. This ensures the selected candidate image is the one that best preserves the identity and structural features of the original object.
Which ensures a high-fidelity reference for the diffusion model to follow.
During training and inference, yes.
So after training on this supervised Illumination-aware Rose plus dataset, what is the key practical outcome for the synthesis stage? What can it do that other models can't?
The model gains true illumination-aware behaviors. Because Rose provided ground truth for both the scene with shadows and the scene without, training on that inversion allows the diffusion model to learn to jointly synthesize the object and the surrounding local photometric variations.
So it's generating physically plausible light interactions.
That's exactly it.
Which means we should be seeing realistic soft shadows that actually fall outside the object mask, or the object's material dynamically reflecting the changing light in the scene.
And the ablation study proves this definitively. They show this fantastic example with an inserted paper bag in a hallway video, and in the video, a door opens and closes, which dynamically changes the ambient sunlight streaming into the scene. Without the Rose plus fine-tuning, the inserted paper bag's brightness and its tone remain almost constant. It just looks flat and detached.
The model is just painting a fixed paper bag texture, completely ignoring the laws of physics.
Exactly. But after training with rows, the illumination on that inserted object dynamically responds. The bag appears significantly brighter when the door is open and sunlight is present, and then it gets darker when the door is closed, resulting in a physically consistent rendering.
And it generates shadows, too.
Yes, the full model learns to infer the global light direction and intensity, and it synthesizes these realistic shadows that correctly extend onto the surrounding surfaces, which is a major, major signal that an object is truly grounded in its scene.
The technical mechanics are incredibly robust. We've solved geometry with a 4D mask, appearance with Roseby++ware. But how does the system actually fare when you measure it against the reigning commercial champions?
Well, this required a serious new evaluation standard. The researchers had to introduce VOI bench, which is a new benchmark necessary for rigorous commercial-grade VOI assessment.
What's in it?
It consists of 50 video clips across highly diverse settings, complex camera movements, varying lighting, dynamic backgrounds, and 100 generated test videos. This allowed them to precisely measure both geometric consistency and appearance fidelity.
Okay, so looking at the quantitative performance across the VOI bench metrics, the results seem pretty unambiguous. InsertAnywhere achieved the highest scores across all critical dimensions compared to Pika Pro and Kling.
They did.
Let's break down what those metrics actually mean for the listener.
Okay, we can start with subject consistency. This measures how faithful the inserted object remains to the original reference object image you gave it. InsertAnywhere achieved the highest CLEP I score at 0.8122 and the highest Dino I score at 0.5678.
And why are CLEP and Dino the gold standard for measuring this?
Well, they're powerful metrics because they measure high-level semantic and perceptual similarity, not just pixels. So high scores on CLEP and DynoEye confirm that the object's identity, its core features and structure is preserved throughout the insertion.
So it doesn't drift or degrade over time.
Exactly. It validates their VLM data pipeline and that first frame anchor strategy.
And for the geometric component, we should look at multi-view consistency.
Right, and that metric verifies how reliably the inserted object is maintained under complex viewpoint changes, camera motion, or, most critically, during occlusions. InsertAnywhere's score there was 0.5857, which was the highest, and that directly validates the necessity and effectiveness of their 4D-aware mask generator.
And if we connect this to the bigger picture, this means fewer geometric artifacts, better handling of those complex tracking shots, and less need for expensive manual cleanup and roto work in a professional post-production environment.
That's a direct commercial value proposition right there. Absolutely. The system also showed superior results in overall quality metrics like background consistency and imaging quality.
Okay, now let's turn to the qualitative evidence. Because seeing where the commercial baselines fail tells us a lot about their fundamental limitations compared to this geometric approach.
The qualitative examples are stunning. They really highlight the structural limitations of these text-driven commercial models. They just lack the explicit spatial reasoning that the 4D geometry module provides.
Let's talk about that specific example involving the wooden drawer case.
Yes. So Pika Pro was tasked with inserting a specific reference image of a wooden drawer case that distinctly had 3 drawers.
Okay, very specific.
Very specific. Pika Pro, despite the reference image, generated a drawer case with 4 drawers, and the color tone was wrong. This shows a deep failure in maintaining subject consistency, scale, and those specific identity features. It probably defaulted to an average training model of a drawer case.
And what about the pepper shaker example, where Pika Pro failed the scale test?
That's another perfect illustration of geometric failure. Pika Pro generated the pepper shaker at this unrealistically large scale relative to the other items on the table. It completely missed the contextual physics and the, common sense size of the scene objects. These failures make the tools unusable for precise virtual product placement.
And Kling struggles heavily with dynamic interaction and occlusion, which is exactly where InsertAnywhere is supposed to shine.
It was a dramatic failure point. In that same pepper shaker example, Kling placed the object in front of a moving hand when, based on the scene depth, it should have been behind the hand. That's a catastrophic failure in occlusion handling. And even more problematically, the researchers observed instances of object swapping, where Kling would replace existing items or even partially replace people in the scene instead of inserting the new object into an empty space.
I can only imagine for a post-production house relying on this, seeing Kling replace a background actor with a handbag would be an absolute nightmare.
And a very expensive fix. It highlights that these text-driven models just misinterpret scene geometry because they lack an explicit map. There's an example in Figure 10 in the sources that showed, despite a highly detailed text prompt, Kling just places a handbag in a physically inconsistent region relative to the depth of the scene. Without that underpinning 4D map, the model can't follow precise spatial instructions.
The robustness of InsertAnywhere really seems confirmed by its modularity. The ablation study drives home how each component solves a specific failure mode.
It's a compelling proof of necessity. They started by trying to use only a simple mask generated by a fixed camera trajectory, the easiest approach. And that configuration failed entirely on occlusion. It resulted in terrible artifacts and consistency fluctuations whenever any movement occurred.
So then they added the core 4D geometric intelligence.
Right. Adding the 4D geometry-aware mask sequence immediately solved the occlusion problems. That confirmed that geometric understanding preserves the ground truth video and movement better than simple projection. But the object's visual fidelity was still low. It hadn't been trained for photorealism yet.
So geometrically sound, but it looked poor.
Exactly. The next step, adding first frame in painting, significantly improved the object's identity and visual fidelity. It looked much sharper. But the temporal consistency still suffered after occlusions. The appearance would briefly fluctuate or shimmer as the object reappeared.
And the final, full model.
The full model, including the crucial LoRa fine-tuning on the Illumination-aware ROSE++ dataset, achieved the geometrically accurate, high-fidelity results with stable, realistic photometric consistency. And the quantitative results back this up. The full model scores highest across all metrics in the ablation comparison.
So it demonstrates you need all the pieces. You need the geometry, the robust identity anchoring, and the illumination awareness for a commercial product.
You need every single piece.
And ultimately, the most important judge is the human eye. So let's look at the user study results.
Overwhelmingly, InsertAnywhere was preferred across every single criterion. For object realism, 79.09% of users preferred it, which confirms its superior fidelity. For lighting consistency, it was preferred by 71.82% of participants.
Which is a massive validation for the ROSE Plus training.
It's huge. It proves its ability to simulate shadows and ambient light in a way humans find convincing.
But the most decisive result, I think, was occlusion integrity.
Absolutely. InsertAnywhere garnered 86.67% of user preference for correctly handling occlusion. It just demonstrates its superior understanding of complex 4D interactions in depth compared to the commercial baselines. That margin is the clearest evidence that when you break down video object insertion into two separate calculated problems, geometry first, then illumination-aware synthesis, you move from high-risk generative magic to reliable engineering that's actually suitable for a production pipeline.
So this deep dive has really highlighted a significant leap forward in AI-driven video content. The key achievement here is InsertAnywhere's successful integration of geometric precision, using 4D scene reconstruction and scene flow tracking to generate a perfect mask. With that diffusion-based appearance synthesis, which is enabled by the specialized, supervised, and illumination-aware ROSE++ dataset.
It's the move from implicit guessing to explicit calculation. Instead of asking one single large generative model to try and guess scale, pose, shadows, and parallax all at once based on a text prompt, they feeded the precise geometric blueprint. They lowered the complexity of the synthesis task, and by doing that, they dramatically increased the reliability of the output.
So what does this all mean? I mean, the future of digital content creation seems to hinge on the AI's ability not just to generate images that look real, but to understand and manipulate the underlying physics and 3D geometry of the real world. This is no longer just about generating convincing textures. It's about modeling reality.
And when the AI achieves that level of physical grounding, it opens up some profound questions.
Exactly. If an AI system can now perfectly place a virtual object, a product, a piece of evidence, an entirely new background structure, and correctly model its shadows, its reflections, and how it interacts with occluding elements, resulting in a placement that is geometrically flawless and photometrically perfect.
Essentially physically indistinguishable from objects that were actually present during filming.
Then the technology has successfully mastered a level of visual deceit that just transcends simple deepfakes.
It does.
So what does that mean for our collective ability to trust any video evidence we see in the future? Even videos that contain no obvious blatant distortions, just subtle, perfect insertions.
Right.
The physical laws of the scene are now manipulable and completely indistinguishable from reality.
It means the standard of visual verification has to fundamentally shift. We can no longer just rely on looking for pixel inconsistencies or weird texture artifacts. We now have to look deeper at the geometric and physical consistency of the scene itself. And that's a challenge very few human observers are equipped to handle.
A fascinating and perhaps slightly unsettling thought to mull over as you navigate the new reality of generative content. Thank you for joining us for this deep dive.
Until next time.